Hello, my name is Stanislas Dehaene. I am a French cognitive neuroscientist. I study the brain, and today I would like to tell you about our research on how the brain learns to read and why it is pertinent for education. My laboratory, situated just south of Paris, specializes in viewing the brain through various means. And I think you are aware now that we have a growing panoply of brain imaging methods, which include functional magnetic resonance imaging, as well as electroencephalography and magnetoencephalography to track the dynamics of brain activity. You may not be aware that these techniques are now available also to study education and to study the child's brain. It is entirely feasible these days with training with a mock scanner and welcoming of children inside that scanner to have excellent images of the child's brain as it is learning, even to do repeated scannings, and these children are extremely happy to come to the lab and participate in this research. All they need to be told is that they are like astronauts inside this spaceship, and that not moving, which is very important for us, they contribute to science, but also contribute to the spaceship not moving. With this, we can study how education changes the brain. I would like to mention in this slide what I think brain science can bring to education. It's a very simple point. I think it's a shame that teachers know more about the workings of their car than they know about the working of the brain of their children. I mean it. I think if you want to change the system, you have to understand how it works and what are the rules of operation. And I believe that empowering teachers with the appropriate knowledge of the principles of brain plasticity and education will lead to better classroom practices. There's a lot we know already in cognitive neuroscience which is relevant. The competencies of the young child for vision, language, numbers, many others. How learning works, the role of attention, the role of reward, the role of sleep, the importance of sleep for consolidation of learning, the transfer from explicit to implicit knowledge, many other topics are relevant. I also think that cognitive science can help measure progresses in education, and experimentation is absolutely essential in order to test education protocols and to quantify their effects on behavior and on the brain. And finally, I believe also that cognitive neurosciences can participate in the development of teaching devices, such as school curricula, manuals, or software. I'll give an example of that at the end. So, today I want to talk specifically about the topic of reading and what we understand about it from the brain's point of view. If you had not learned to read, any page of text would look to you like this stone, a texture, but no meaning. But because you've learned to read, you can have a conversation with the deceased. You can speak to the dead, you can listen to the dead with your eyes, because you can read what they wrote 2,000 years ago. You can communicate thoughts to the mind through the eye, which is the great invention of the world, according to Lincoln. So how does that work? Well, this is a picture of your left hemisphere. The left hemisphere of the brain is most essential for language and reading. And just to orient you, this is the back of the brain, this is the front of the brain. It's been slightly inflated, so you can see inside the folds. And now I want to show you the activation of the brain as you read one word. We see it in time. So let me start this. Here we go. And you have the word unfolding from the back of the brain to the front of the brain. It will loop several times. You can see the information enters into the occipital pole, which is the visual side of the brain, moves into the ventral areas, and then explodes into the left hemisphere distributed activity. I have no time, of course, to explain to you all of the details of this brain activity, but I want to show you a sort of caricature that you can remember. And this is very simply that reading starts as any other visual stimulation in these generic visual areas of the occipital pole of the brain, but then very quickly moves into an area that we have discovered, which concentrates the recognition of the written word. I have called it the brain's letterbox, because it is where we store our knowledge of letters. And from there, what you have seen is this explosion of activity into at least two networks, one that concerns the meaning of the words, and another that concerns the pronunciation and the articulation of the word. And so we can say essentially from the brain's point of view that learning to read consists first in recognizing the letters and how they combine into written words. And second, connecting them to these systems coding for speech sounds and for meaning. And what is rather remarkable is that all of the areas in orange and in green here already exist for spoken language. They are shared between spoken language and written language. So not only that, but they already exist in a young child. We can image the brain of young babies, even when they are extremely young, few months of age. We have various methods for that. And when we have them listen to language, we already see this network of regions which exist also in the adult brain and that process spoken language. So we may say that reading is not creating something completely novel. Reading consists essentially in connecting, creating an interface between vision and the language system, the spoken language system. When the child comes to the reading school, it already has a very sophisticated spoken language system. It already has a very sophisticated visual system, but it needs to create this interface, this visual word form area, this brain's letterbox, and to connect it appropriately. And in doing so, it needs also to change some of these target systems. How does this work exactly? We've conducted a large number of studies, and many other labs in the world have conducted many studies that look at what has been changed in the brain of children or adults after they've learned to read. And in particular, I want to mention here a study that we did very recently, which was published in the journal Science, where thanks to a large international collaboration, we were able to scan illiterate and literate subjects of various levels of literacy in Brazil as well as in Portugal, bringing them to our lab in France. Thanks to this experiment, we managed to make a complete map of the areas that have been changed by learning to read. And as all of you in this room know how to read, you can consider that your brain has been dramatically changed. So I've told you about these areas for language. The first major change that we see in the literate brain is this letterbox area coming active only in people who have learned to read. It will activate in direct proportion to the reading score, and it will activate to the letters that you know. It will not activate, for instance, to Chinese if you don't know Chinese. So it has learned the shapes of the letters. It is accompanied by major change in the visual cortex, in your early visual areas, which is generic and serves for all sorts of visual tasks. You have changed the precision of the coding in your visual cortex because you've learned to read. But most importantly, you have also changed your representation of speech sounds. If you've learned an alphabetic language, you have changed the way your cortex codes the phonemes of speech, the elementary components of speech. And learning to read is to a large extent the capacity to attend to the individual phonemes of speech and to attribute them different letters. When we see this map, of course, we could think that the connection between these areas must also be changed. And I'm happy to say that with new methods for identifying the connections of the human brain, we can also track these changes. We can see, even in a living person, all of these fiber tracks that connect different brain areas. We can see their microstructure. And what we see is that, indeed, this particular connection bundle which exists in all brains is reinforced and is being changed in people who have learned to read. And there is a good likelihood that this bundle is involved in connecting the letters to the sounds bidirectionally. When you hear a sound, you can also think about these letters. This change is subtle, but it is an anatomical change. So the anatomy of the brain is also changed because children learn to read. We make these essential changes that, of course, create a whole new modality of input of language. There are lots of things we've understood about the details of this process. I want to give you a few. The first thing is, what does this area do before we learn to read? It's, of course, not an area that has evolved for reading, so it must be doing something else. And what we have found is that this region reacts also to faces and to objects. It is involved in visual recognition in all species, actually, in all primates at least. And what we find is that as you learn to read, so this is reading score on the x-axis here, what you can see is that the response to strings of letters increases in this area, but the response to other categories decreases. So there is a sort of competition in the brain of the reader, and the new function of reading has to find some space in the cortex, making room, as it were, and what we find also is that the representation of faces is therefore displaced to the right hemisphere. Words compete with faces in the reader's brain. It's not a massive computation, but it is a sort of reorganization which takes place when children learn to read. Thanks to this understanding, we can also explain puzzles of reading acquisition. And one puzzle which we have been able to explain from the brain's point of view is something you might have seen in your children, which is this notion of mirror reading and writing. Many children, when they sign their drawings, will write their names in the improper direction, from right to left in this case. Here is another example of a child who has written Theodore ti voglio bene, okay? And the child is writing left to right to left, alternating in a writing system which is called boustrophedon, which means how the ox plows. This was the way of writing in ancient Greece. But of course, children don't know about ancient Greece at that age. So how are they capable of doing these things? And many parents think, is this dyslexia? Well, we understand now what it is. It is not dyslexia. What it is a trace of this old function of the system which is trying to learn to read. All primates have a symmetry mechanism which allows you to notice that these two faces are the same person, even though on your retina they are completely different pictures, but they are mirror images of each other. And this is an evolved system that we have to unlearn as we learn to read, because it is not useful, and we have to distinguish these things as two different words or potential words. We have found indeed that the primary area which has the most sensitivity to this symmetry is precisely the area that I've called the brain's letterbox, which is trying to learn to read. So essentially, it's not a wonder that children have difficulties with mirror reading and writing. This has nothing to do with dyslexia. It is a universal difficulty for all children that they have to overcome, and we might teach them explicitly by the gestures of writing to help them to overcome their difficulty. Another thing that we understand a little bit better now is this very classical question of phonics versus whole word training. You know, there's been a lot of debate in psychology and in education. Should we teach the whole word level, or should we really teach every single letter and their pronunciation? Is there anything such as the global shape of the word which is being used in reading? Well, here there is something very important. As adults, we have forgotten how we were as children. We have forgotten how difficult it was to learn to read, and we think that we can just lay our eyes on a word and it immediately pops to mind. And indeed, there is this notion of parallel reading. We read all of the letters at the same time. This gives us an illusion of whole word reading. But in fact, if we look at the brain still processes every single letter and does not look at the whole shape. So whole word reading is a myth, basically. What we have is letter processing, but letter processing in parallel across all of the letters of the word. The brain does not use the global word shape. And in fact, in children, it's even worse. Children require more and more time for more and more letters. You can see this on this graph. This is the number of letters in a word, the reaction time of the children. And in first grade, they're very, very slow, and they need more and more time for each letter. So this is not at all whole word reading. It's slow, serial, one letter at a time. And as children progress, second grade, third grade, this goes away and gives this illusion of whole word reading. So I think we can be very clear on this point, because there is a strong convergence with educational research to suggest that the brain has nothing to do with this sort of exercises that my child had of picking up the ascender and descender letters and deciding that this corresponds to this word. The global shape is not used. Few words of conclusion, few slides of conclusion. I think neurosciences can help education. We understand now a lot about reading, and we understand that in all cultures, there is not so much variability. We always have the same brain mechanisms. Reading always requires specializing the visual system for the shape of letters and connecting them to speech sounds, even in Chinese, by the way. There are no letters, but there are characters, and some of them map statistically to the sound. Teaching letter to sound correspondences is therefore essential. It's one of the main pathways which is being transformed in the brain. Brain research converges with educational research teaching of letter-to-sound correspondences is the fastest way to acquire reading and comprehension, not just, being able to decode the words. How does this work? Because it works because there is a form of self-teaching. Once the correspondences are learned, children have this correspondence between letters and sounds, then they can recognize the words auditorily using their auditory lexicon, and then this more direct route between letters and meaning can be trained. It can be self-trained as the child reads by himself, even without a teacher. So this notion of two routes of reading play a very essential role in all contemporary models of the reading process. Cognitive neuroscience can also lead to new software tools, and very briefly I want to mention that our colleagues from Finland have been developing over many years now this graphogame, sophisticated software, which is just looks like a game to children, where you have to select letters based on the sound that you hear, and many training games of this sort, and they have shown that just a few hours of training with this little game suffices for preschool children to already begin to develop this visual word form system that I've been talking about. So with efficient tools that attract the child's attention and reward them for what they can do, we get very quick changes in these plastic brains at this young age. I want to mention that this notion of neuronal recycling, the idea that some areas are sufficiently plastic that we can shift their function slightly, which is what occurred during reading, is a sort of general principle. We all are like this caricature of Darwin. We are humans, but we are also primates. And as primates, we inherit constraints on our brain. Our learning is constrained by the representations that we inherit from evolution, which concern not just language, but also number, space, time. And teachers must take into account this early child's knowledge, because if we understand what they have to displace in the child brain, we can teach better. I want to mention that this is relevant to reading, but also, I think, very strongly to mathematics. We begin to understand that our brain, the human brain, just like other monkeys, is organized to understand concepts of the external world, such as number. And the same brain areas that are concerned with number in the monkey and in the human brain. And on this basis, we can begin to understand what is the foundation of intuition of number sense that develops later into a full system of arithmetic. And so on the very same principle of this notion that there are old brain systems that need to be recycled, we can propose an understanding, a beginning of an understanding of the development of arithmetic. And I want to mention that this is just culminating now in my lab in the development of software tools that are based on cognitive principles and that can help children develop a better sense of number. And this number catcher software is just available today. It's called the numbercatcher.com, and it's a new software that's freely available in order to help children develop their intuitions of number. Finally, I want to finish by saying that you can read about these topics in more detail. I realize that 20 minutes is not sufficient to convey all of these ideas, but primarily now I think we can have a short discussion. Thank you very much for your attention.